higher. So this video is about the sum to infinity of a geometric series. Doesn't that sound amazingly fantastic? The sum to infinity. What does that actually look like? Let me just give an example. So I'm just going to start with a simple number, 1. Okay, and then I'm just going to divide each successive term by 3. So the common ratio is 1/3. Yeah. So the next term is 1/3, and then divide that by 3. I'll get 1/9, and then divide that by 3. 1/27, 1/81, and so on. Okay. What's happening to all of those terms? Well, they're getting smaller, smaller, and smaller. Will the term ever reach 0? Well, technically no, because you can't keep dividing a number by 3, then end up at 0. But at infinity, you can. That's essentially what's happening at infinity. At infinity, essentially all these terms are just getting closer and closer to 0. Okay, we say that the limiting value of each term is going to be 0. What that means is you can add all these terms together. If the little terms are getting progressively smaller in this way, you can add them together. And that's what we call an infinite summation of all those numbers. Okay, and that's what I'm going to talk to you about here. So this is a geometric series. So we'll begin with the sum formula for geometric series. A 1 minus r to the n over 1 minus r. Doesn't work. Don't forget when r equals 1. That's a simple case though, isn't it? R equals 1. Basically each term is the same. So you start with 5, and then if common ratio is 1, you've got 5 plus 5 plus 5 plus 5 plus 5, and you can just do that by multiplication. So here I'm just going to rewrite that by splitting it up into 2 separate fractions. So what I'm doing is I'm taking the a times 1 bit and writing it as that over 1 minus r, and then the subtract a r to the n bit over 1 minus r. Okay, so that's what's going on there, just expanding the brackets and converting it into 2 separate fractions. Okay, this followed by this. Right, now when you have a convergent series, as it's called, as each term gets progressively smaller, you can do it. When you've got a divergent series, you can't. Okay, so let's just suppose you have this series, a very common series, 1 and then 2, 4, 8, 16, 32 and so on. All the numbers are getting bigger and bigger and bigger and bigger. So there's no actual sum that you can actually find for an infinite number series of terms because each term is getting progressively bigger. So you can only actually do this for when you've got r's between -1 and 1. Okay? So when you're dealing with a series sum that you can find to infinity, you're dealing with r's between -1 and 1 because the terms have got getting smaller and smaller. They can be negative. So in my previous example, I divided them by 3, so r was a third. You can also multiply by -1/3, and the terms still get smaller and smaller, converging on the number 0. Okay, we sometimes write that like this. This is a different way of writing it. Okay, this means the modulus of r is less than 1. Basically, what it means is that r, whatever it is, the absolute value of it is smaller than 1. These mean exactly the same thing. Okay. Consider what happens when you've got this scenario when r lies between -1 and 1. Consider what happens to this term here. I'm just going to bring it down by here. R to the power of n. Well, if r is a fractional value, like 1/3, like I had earlier, if you just raise that to the power of 2, then 3, then 4, then 50, then 100, what happens to this? It gets smaller and smaller and smaller, doesn't it? R to the power of n actually gets smaller and smaller and smaller. That's at infinity. It tends towards 0. We write that as this. R to the n tends towards 0 as n tends towards, that's an awful infinity sign, but I'm going to keep it because the video is rolling, as n tends towards infinity. Okay? Try it with any fractional number between -1 and 1, not inclusive. If you do that number in your calculator to the power of 50, to the power of 60, to the power of 100, it gets progressively smaller towards 0. So what does all that mean? That means that this is essentially 0. Okay, let me just uncross it out again. Okay, because you've got r to the n is 0, times by a, still 0, divided by another number, still 0. So all of that is going to be 0. So what that means is you've got this left over, a over 1 minus r. Okay, this is just neatly written. Okay, a over 1 minus r. And that is your sum to infinity. Okay, that is your sum to infinity, only for, as I said, a convergent series. That is when modulus of r is less than 1. Let me just give an example of how that works. Here we go. So this is actually a question that I remember being asked when I was in my first year of senior school. It's called year 1 at the time. It's called year 7 now, but yeah, that's by the by. I was asked this question, okay, well, the whole class, not just me personally. It wasn't just a personal math lesson. The whole class will ask this question. Okay, a fog jumps or wants to jump from one side of the pond to the other, but each time the fog jumps, they can only jump half the remaining distance. Okay, so it's worded up here. Okay, so the first time the fog jumps, this is the length of the pond. The first time the fog jumps, they're going to just jump to the midpoint here, and then each successive jump, the fog jumps half the remaining distance. So this is the total distance left. So the fog is going to do a next jump to there, and then this is the remaining distance. The fog is going to jump to there. So the question was, will the fog ever get there? How many jumps will it need if it does actually get there? Okay? That was the question. Yeah? So you can think about it mathematically or in terms of diagrammatically. The fog is getting closer and closer, but there's always going to be a small gap, isn't there? Admittedly, in real life, the fog can then just hop over to the other side once it gets close enough. Okay? But mathematically, there's always that really, really small but narrowing gap. Here's what we do with maths. We tend to convert a real-world problem into a mathematical problem using numbers. Okay, so let's do that. Okay. So the first jump the fog makes is half the remaining distance. So that's that there. That represents 1/2. And then half the remaining distance again. So that's going to be a quarter, isn't it? So you've got half the distance remaining. Half of that is 1/4. So the fog is now going to jump 1/4 of the pond. And then you get the idea. The next leap the fog will do will be 1/8 of the pond. And the next leap the fog will do will be 1/16 of the pond. And then 1/32 of the pond. And of course, that gap is getting closer towards zero. It's getting to a narrower gap, isn't it? This is what we call a convergent arithmetic series. And you can do a sum to infinity of that. Okay? The sum to infinity works using the formula a over 1 minus r that I just mentioned to you, where a is the first term, that's 1/2. So half, and over 1 minus the common ratio, all of these are multiplied by 1/2. So that's going to be half again. 1/2 divided by 1/2 is just 1. 1. So that entire series sum to infinity adds up to 1. Which, if you think about it, makes sense, because 1 is basically the length of that pond. It's 1 pond. Okay? So I just thought I'd give you that example because it's a nice one to show you how a sum to infinity works. But seriously, you can use that summation formula for any geometric series as long as it's convergent. Well, thank you very much for watching, and I hope you found that interesting. See you again.